Is it working? All right. So what we're looking at is the works of Cuso and Pilanetto, 2012. We're looking at large-scale dynamical networks, and we're looking at one input at a time. And we have this input-output model. We have a lot of variables, but it's sparse. And so even though we have a lot of variables, we only need a few to predict y. And so the problem is to select which ones. And so we have equations for the predictor, and we're going to impose that the predictor is from a reproducing kernel Hilbert space, and we've chosen the kernel to be this exponential thing here. So it is positive definite. If beta is too large, it will be computationally not positive definite, which I found out the hard way, but it's positive definite. So the individual predictors, we're going to say, they have the same covariance kernel, but just scaled by a lambda I. And so now all we need to do is find the lambda i's, and what we can do is find the causality graph. I don't think it's a real graphical model in the sense that we've been doing, but we're going to encode it so that if we need ui to predict y, then there's a link, there's an edge there. So the solution is to minimize this functional, which is the negative log likelihood of a Gaussian. And it's non-convex, it's high dimensional, but they had good luck with it. I don't know, they must have run it for like 3 weeks, but they had good results with it. They also have an easier problem. You restrict that all the lambda i's are the same, and then you use forward selection to select which of the lambda i's are greater than 0. And that works well on its own, but also works as a good starting point for the full problem. But what they also mentioned in a kind of a blurb at the end is that you can exploit the spectral decomposition of this kernel. And they've done this for a single input case, but they hadn't done it for this big multiple input case that we're looking at. So that's what we implemented. And we found that we have these 3 graphs here. The first one was the biggest system that we could do without spectral decomposition, and so we had an identification set, a validation set of 100, and so we couldn't get as good of this is the R² value of the predictor, couldn't get as good results with a validation set of 100 as we could with 1,000, but we couldn't have run the 1,000 without spectral decomposition. So, and you can see over here is the number of eigenvalues that we used, and I don't know why there aren't labels here. There were. But we have on the x-axis the number of eigenvalues, and then on the y-axis the coefficient of determination. So you can see the more eigenvalues that we use, the better results we get. But we can still get good results with a few eigenvalues. So, that's it. I didn't go over, did I?
No, I think so.
All right.
The question